Uh, Hello everyone, welcome to today's talk, Beyond Propensity, getting from traditional machine learning to uplift modeling. Give you a brief agenda of what we're going to cover. So I'll first do a short introduction to faculty. I'll then tell you what is uplift modeling, what are some of the challenges it solves, then tell you why it's hard, what methods are generally used to do uplift modeling, and give you a flavour of some of the research we're doing at faculty to make these methods rise to the challenges better, and then there'll be time for Q&A at the end. So feel free to ask questions throughout using the Q&A function, but I won't answer them as we go along. I'll answer them all at the end, so I'll leave enough time to do that all at the end. So first of all, who are we? Who are faculty? For those who don't know, we're a company that exists to make AI real. So we believe that the fantastic developments coming out of research and academia are only really living up to their full potential once they're deployed safely and robustly in the real world. We've been doing this for a number of years now, and we've worked in a bunch of different sectors for many different customers. I'm Gary, I'm the lead data scientist in our consumer business unit, where we focus on consumer problems. So we tend to work with, for example, retailers, e-commerce, travel, telcos, consumer goods, and the kind of techniques I'm going to talk to you about today tend to be, not exclusively, but particularly applicable in those sorts of sectors. So when you have companies who are interacting directly with their customers. And of course, this isn't just all theoretical stuff. This is stuff that we have and we do implement in the real world for our customers. And if you think that any of the stuff I'm talking about today might be of interest to you, please do get in touch. There'll be contact details at the end. So first of all, what is uplift modeling, and kind of what are the problems it solves? So hopefully the thing I'm going to say at the beginning of this slide isn't too controversial. So I'm not going to try and say that machine learning equals supervised learning. That's definitely not true. Machine learning is quite a broad field, but I'm going to posit that most machine learning models that are in production in the economy today are actually supervised learning models. And moreover, I might go a little bit further and say that most are probably classification models. And I think I'm confident going even a little bit further and saying probably most of those are binary classification models. And that will be the thread that I use throughout today. So what's a binary classification model? It's a model that takes some known inputs and tries to predict an unknown, like, is this an A or is this a B? Or what's the probability that this is an A? What's the probability it's a B? And this clearly is useful some of the time, but also it's not going to solve any problem you might have. And in the kind of problems that we work in the consumer space, I would go a bit further than that and say most of the problems that we try to solve are inherently counterfactual, and prediction isn't quite the right tool if you're trying to solve a counterfactual problem. So what do I mean by this? Well, generally in the consumer space, our customers are trying to interact with their customers, and they want recommendations of how to do that in a better way. So they don't just want to know what will happen next. They want to know, how can I change what will happen next? Or a little bit less abstractly, like, how can I get my customers to buy more of my stuff, more of my services? So first of all, let's go to when predictions can be useful. So this is kind of a pretty obvious example. If I see this weather forecast, and if I live in Glasgow, I might say, today I will bring my umbrella with me when I leave the house. And this is just obviously a prudent thing to do. And the reason it works nicely, it's kind of so obvious that it almost doesn't bear saying, but if I take my umbrella with me, that doesn't have a feedback loop. It doesn't kind of affect the weather in any meaningful way. So when I see it's going to rain, I take my umbrella, I don't change the weather, I remain dry, everyone's a winner. So now, welcome to the consumer world. So first of all, I'm going to go through an example where prediction might be useful, but this is probably actually the example in the consumer world where I hold out the most hope for prediction, but we'll still see it's kind of a maybe. So this is the case of churn modeling, which is particularly used in businesses that have subscription models. So for example, telco or broadband providers. And they train models which tell them how likely somebody is to churn at the end of their contract, how likely they are to not renew. And they do this using supervised learning. So it's a binary classification problem. Will they leave us? Will they stay? And based on some input feature vector, which might be things like how much are they paying, how long have they been with us, have they had any problems, have they kind of got in touch with the customer service center, etc. And your model might then say, here's a person who has a 70% chance of churning, and here's somebody who has a 30% chance of churning. And the way this tends to then get operationalized in practice is people get on the phone and call the person who's more likely to churn. They go and call the 70% person and offer them a discount. Say, if you sign up again, we'll give you a discount. And this might be useful, but let's go into what some of the difficulties are. So generally, we say the person is likely to churn, we're going to call them. And the problem is we tend to think of this in a very human way, which is, oh, the model says 70% likely to churn, and that means they're thinking about churning and they haven't really made up their mind yet. But statistics actually tells us to interpret this in a different way. Statistics tells us that if we find 10 people in our data set who have a 70% chance of churning, 3 of them will not churn and 7 will. And this is just what's known as unexplained variance. The 3 who do and the 7 who don't will differ in ways that we just can't see in the data. So for example, somebody might have just got a new job, which pays more money, and they want a more premium service, which we don't offer. Or perhaps somebody's thinking of moving abroad, or perhaps somebody has a friend who's had really bad service issues, or perhaps a friend who's had really good service issues. And these are all things that exist in data that we can't really capture. And the result of this is that there will be 3 people who don't end up churning for reasons that we just can't determine from our data, and 7 who do. But if we call all 10 of them, well, the first thing that happens is the 3 people who wouldn't have churned say, oh, thank you very much. You've given me a discount, I'll sign up again. But the reality is they would have done so anyway. So right off the bat, you've given away margin. So for this to be worthwhile, you better hope that the discount that you're offering changes enough of the remaining 7 minds to A, win back the margin you've lost, and then B, make you some more money, pay off the cost of the call center, the modeling, etc. And basically that depends on a variable that you don't really have access to, which is how much do you have to offer a discount? How much discount do you have to offer to change people's minds? There's another thing in here, which is how discriminant is your model to begin with? So if this group of people didn't have a probability of 70% of churning, but 90%, then you'd have less of a problem because you're only giving away margin on 1. You have to change fewer minds to win back that margin. So it depends on 2 things. It depends on how discriminant the model is, which basically means how much signal is in your data, how good is the model. I guess that's something you sort of do have access to. You can see what kind of predictions the model's making. Does it tend to predict 70-30, or does it tend to predict 90-10? Then it also depends on how much of a discount you have to offer to sway people's minds, and how those 2 effects trade off on one another will tell you kind of how good, how useful this churn model is in practice. Remember, this is kind of the best case scenario. A lot of the consumer world looks like this. So especially in e-commerce, a lot of companies have lots of people who bought from them before, maybe once, maybe twice, maybe 3 times, and they haven't bought in a while. And what they can do is train models which tell them how likely these people are to come back again. So what's the probability they'll buy in the next 6 months, in the next 12 months, in the next 24 months? And those models will tend to be based on recency frequency metrics, standard marketing metrics. So how long has it been since they last made a purchase? How many purchases have they made before? What's their lifetime value? Perhaps, what were their return rates? And this is relatively well understood how to do because it is just binary classification. And you train a model, and your model says, okay, this person has a 10% chance of coming back, and this person has a 4% chance of coming back. So you could take the analogous approach to the one we took for churn modeling. And in that approach, you'd say, well, the person who has a 4% chance of coming back, they're pretty unlikely to come back organically. So let's send them an offer. Let's send them an email that says, we miss you, £20 off your next purchase. Sounds familiar, right? This is fine because it's low risk. But what tends to happen is that people who haven't bought in a while tend to be the people who are less likely to come back. So a simplified version of the world says, the longer it's been since you've last purchased, the less likely you are to come back again organically. So if you tend to focus on people who are unlikely to come back organically, you tend to be focusing on people who haven't bought in a while. And our experience and that of our customers shows that it's just hard to change these people's minds. You can send them a £20 off offer, and it doesn't tend to make much difference. So it's low risk as long as you're doing this via email. It's a whole other matter if you're communicating via, say, direct mail, and the act of sending it costs you. But if it only costs you if they redeem, then it's relatively low risk because you're not cannibalizing your margins very much, but it's also relatively low reward. And really what you want to be doing is focusing here. You want to say, well, people who have bought more recently, are more likely to be swayed by our offers. But the problem is they're also more likely to purchase organically, and you might just end up sending offers to people who are going to buy anyway, and again, giving away the margin. So what to do? This is basically the central problem of various types of marketing, which is you want to only market to the people for whom it's going to make a difference. You want to find people's probability of buying if they do receive an offer, their probability of buying if they don't receive an offer, and you want to find only the people for whom you're making a big difference. So if they're going to buy anyway, don't send them an offer. If they're not going to buy either way, probably also don't send them an offer. These people in the upper left quadrant you care about. And of course, you can replace probability of purchase with expected spend, and everything I said is still true. You want to get in touch with people who, on average, are going to spend more if you do get in touch with them than if you didn't. So if we write this down in equations in standard supervised learning, what we want to do is make a prediction. In this case, we always use hat for prediction. So yi hat would be the probability that the ith individual is going to buy. We want to do that using a vector, which is the stuff that I have access to right now. So how long has it been since they last made a purchase? What's their lifetime value? Possibly some demographic stuff, if you know where your customers live, etc. And you want to learn this function f. In counterfactual modeling, what you want to do is say, well, I could take a number of actions, and we tend to borrow from the medical literature and refer to these as treatments. I could treat each of my customers in a number of ways. So this could be binary. It could be I could send the offer or not, or it could be I could send no offer, or I could send offer A, offer B, offer C. And in each of these cases, I want to predict what my customer will do. So I want to learn this function, which again is a function of this xi vector, the stuff I have access to but no control over, and the treatment, stuff I have control over. And then for any individual, I can say, well, what if I did treatment 1? What if I did treatment 2? What if I did treatment 3? Interrogate the model, find out what's likely to happen, and then choose the scenario best for that individual. So that's what counterfactual modeling is. And the way you've written it, it looks like a pretty trivial rewriting of standard supervised machine learning. So let's talk about why it isn't, right? If it were just a trivial rewriting, then this would be a pretty short talk. I'd basically be done now. There's 3 reasons: confoundedness, signal weakness, and difficulties in doing cross-validation, which is basically signal weakness again, but it's so important I thought I'd give it a new subsection. So what do I mean by confoundedness? So this is what's known as a causal diagram. So if you've not seen one of these before, I think they're fairly intuitive, but I'll just give you a brief overview of how to read this. So in this case, again, X is as X was on a few slides back. It's stuff that we know about but have no control over. T is the treatment, and Y is the outcome. And what this diagram is saying is that X has a direct influence on T and a direct influence on Y, and T has an influence on Y. So why might this happen? Well, most businesses, in the data they collect, they were not doing random stuff while that data was being collected. They were marketing in some way according to business rules. So let's use a simplified example of an e-commerce retailer that, when you haven't bought for, say, a year, sends you an email that says, we miss you, £20 off your next purchase. So what that's saying is, if we think of X as just time since last purchase, X has an impact on T. Right? People with low time since last purchase don't get the treatment. People with high time since last purchase do get the treatment. Also, X has an impact on Y. People who haven't bought in a while are less likely to buy. And T has an impact on Y. Presumably, people who get the offer are a bit more likely to buy than people who didn't get the offer. And this is what's known as confoundedness. You want to measure the impact of T, but it's difficult to measure the impact of T because there's this indirect impact from X coming via T, but also a direct impact. Confounders generally, for uplift modeling, present what's known as a manifold problem. So they don't bias your analysis, they just make it unreliable and noisy. So in this e-commerce retailer example, if you only ever send offers to people who've been inactive for more than a year, you have no way of knowing what would happen if you sent an offer to someone who'd been inactive for 6 months or 3 months. And the problem is that your machine learning model will still just blurt out some answer, and it won't necessarily blurt out that answer with any lower level of confidence. So it's quite tempting to just take it at face value, but the reality is it's unreliable. I don't want unknown confounders to be the topic of today's talk, but I'll just give you a brief introduction to like why they're a problem. So unknown confounders can and will introduce systematic biases into your predictions. And the best example I can think of this is if you were trying to do this sort of analysis where the treatment is paid search, and you're trying to understand how well paid search is working. So the unknown confounder here could be something like, I ripped my jeans yesterday. So that's a variable that clearly might affect how likely I am to buy some new jeans in the next couple of days. But it's not really data that anyone's going to have, right? It's hidden data, it's a hidden variable. So somebody who has just ripped their jeans is much more likely to open their search engine up and search some jeans related term. They're thus much more likely to see a paid advert, much more likely to come onto your webpage via a paid advert. And those same people who come on via a paid advert are much more likely to buy something because they ripped their jeans. But because you can't see that they rip their jeans, you just see, oh yeah, people who come in via paid search buy more. You can start to conclude that paid search is wonderfully effective. Now, I'm not trying to say that it's not and it doesn't work. I'm just trying to say this sort of analysis will most likely tell you that paid search works incredibly well all the time. And any analysis that tells you that something works really well all the time without any caveats is probably flawed. So from confoundedness to signal weakness. So what I've done here is tried to come up with the most simple model of the world I could that exhibits the point. So I've said, imagine you are a retailer who wants to send out their beginning of season catalog, which perhaps is slightly retro, but bear with me. And I've come up with this distribution that says there's one feature, just to make life simple, and the probability of purchase is impacted by that feature. And I've called it feature. I've sort of remained intentionally abstract, but really I mean something like time since last purchase. So again, people who haven't bought in a long time are less likely to buy again. People who receive catalogs are more likely to buy than people who don't receive catalogs. And there's a differing effect in the way this stuff tapers off over time. And when I take the difference between these two charts, the point is you get something not entirely trivial, right? It's not just catalogs become less effective over time or more effective over time. It sort of goes up and then down and there's a sweet spot. And of course, it's a somewhat contrived example, but perhaps you might say, okay, based on average order value, I think that the catalog is only positive ROI if the probabilistic uplift is more than 2.5%, and thus I need to hit people in this gray regime. So what I've done is I said, okay, let's synthesize some data from these distributions and then use machine learning to see if we can learn the underlying distributions that created that data. So on the left, the blue line is the blue line from this chart, and the blue line on the right is the orange line from the previous chart. So it's just the probability of buying if you receive a catalog or not. And I synthesized some data from these. So what I did was I first of all sampled feature, which I took from a gamma distribution. So I got lots of feature values, basically between 0 and 800 roughly. I then said, okay, half of them get a catalog and half of them don't. So for the ones that get a catalog, I know their probability of purchase. It's pulled from the blue line on the left. And for the ones who didn't get a catalog, their probability of purchase is pulled from the blue line on the right. So now for every individual, I have a probability of purchase. I then toss the computational coin and figure out whether they do or don't buy. It's a Bernoulli process. So now I have some data which has 3 columns. Column 1 is feature. Column 2 is what's known as treatment, or did they or did they not get the catalog. And column 3 is a binary, did they buy or did they not. I split the data into 2, the people who got the catalog and the people who didn't. And for each of them, I just train a standard supervised learning model to learn how likely are they to buy. And the result is this jagged orange line. And you might initially look at that and say, that's not very good. Or you might say, okay, I see what you've done there. You've trained a random forest to fit a distribution that's like clearly exponential. That doesn't sound very smart. But this is also a pretty contrived and simple example, right? The real world is not univariate. There'll be multiple features, they'll be interacting. And the reality is you probably do need to train something like a random forest. And the reality is that even if the true data generating distribution is smooth, your estimate of it will be something jagged like this. And actually, if you use any standard metric like test cross entropy, you would find that the orange lines are doing pretty well to approximate blue lines. They're learning the broad features, right? Like at 400 days, you're 4 times less likely to purchase again organically than after 100 days. So it might not obviously look good, but broadly speaking, these orange jagged lines are approximating their blue lines well. So supervised learning is great and it works, hooray. Problem is, when you take the difference of these signals, which should be the uplift signal, that works less well. So that is just a big old mess. And you can't really do much with that. So in maths, what we've done is we're trying to learn the uplift signal, which is the probability that someone will buy given their feature vector, or just their feature scalar in this case, and given they got marketed to, so m equals 1, and subtract off the probability they'll buy given x, how long it's been since they last purchased, and m equals 0, they didn't get marketed to. And we learn these two functions with two different supervised learning models, f of x and g of x. And this is this thing u. And then I say, what's the standard error on u? Well, the standard error on u is given by this quadratic term here. So errors out in quadrature, because f and g's errors are uncorrelated. They're trained on different data sets. And that means that the fractional error on u is much bigger than the fractional errors on f and g. This is just a general thing in statistics. If you have two uncorrelated variables, the standard error, the difference between them, is of the same order of magnitude as the standard error on the original quantities. Whereas if these two random variables tend to be very similar in size, their difference could be an order of magnitude lower, 2 orders of magnitude lower. And this is really, to me, the central problem in Uplift, is that you're looking for a signal on a signal. And that means that the ultimate signal you're looking for is much smaller, but it turns out the error is of the same size. So fractionally, your error can be enormous. Finally, third challenge is in cross-validation, which is basically signal noisiness again, but I thought it deserved its own section. So why is cross-validation important? So in standard supervised learning, I give you some data and say, tell me what model I need to deploy. And you train your logistic regression, and you train your random forest, and you train your XGBoost, and you train your neural network, and you tell me, yeah, okay, what we need is XGBoost, and we need it with these particular hyperparameters, right? So cross-validation is something that you need to do model selection and deploy the right model. And for binary classification, the way it works is you have a test set, and you take models, you ask for each model, you look at the actual outcomes in the test set, how likely were those outcomes according to your model? And models which, on average, say that the stuff that actually happened in the test set was more likely to happen are better models. Or more mathematically, we sum over the test set, and we take the logarithms of the probabilities according to the model of the events which actually happening given their features. The reason this works is because you're getting some feedback from the real world. The real world is telling you what actually happened. But Uplift is a counterfactual quantity. So we want to know the probability that someone will buy, given they got marketed to, and subtract off the probability they will buy, given they didn't get marketed to. But that's counterfactual. In reality, either they did get marketed to, or they didn't get marketed to. The universe isn't giving you feedback and saying what would have happened in either scenario. And if it were, this would be a hell of a lot easier. So what do people do? Well, you need to use some sort of empirical scheme where you bin people together. And this is only going to work if you don't have confounders. So even known confounders will mess this up. So you need what's known as randomized data. You basically need to run some sort of randomized control trial. And the reason for this is that what you then do is you take all of your customers in a test set, you rank them by their predicted uplift, and then you do some sort of binning scheme. So let's say you look at the top 5% of people according to their predicted uplift. If you've run a randomized control trial, some fraction of those people will have got the treatment, or they got marketed to, and some people will not have got the treatment. So within that bin, you look at, for the people who did get marketed to, what fraction of them bought. You look for the people who did not get marketed to, what fraction of them bought, and you take the difference. And that's what's known as the empirical uplift, the observed uplift in that bin. So then you basically calculate the observed uplift in each of the bins, and you can see how well it does compared to the predicted uplift. And this gives you some way of seeing how well your model's doing. And then you can compare this between models. But there is a catch. So what I've done here is I've simulated some more data in which the true uplift signal is known. So I have just said, there's some distribution of features. I write down some equation which determines the true uplift. I then say some people got the treatment randomly and some people didn't. That allows me to calculate their probability of buying. I then sample from a Bernoulli distribution. And then I do some sort of binning scheme where I bin people into high uplift bins and low uplift bins, and actually calculate this observed uplift per bin. And to be fair, to really ram this point home, I've done it with the true uplift signal being small, because this is all much worse when the true uplift signal is small. But in the real world, it often is, right? Especially in marketing. Like marketing only makes you a bit more likely to buy, doesn't make you twice as likely to buy as you otherwise would have been. So the issue here is that observed uplift often looks nothing like the true uplift, right? It does if you have a ton of data, as on the right, like fine, if you can sample 2 million points, that's all very well and good, but that means you have to run a trial of size 2 million. So why is this important? Why? So if observed uplift doesn't look like true uplift, well, if I go back a slide, we're going to here say, I want to know what the predicted uplift is. I want to compare it to the observed uplift. And the implicit assumption here is the observed uplift somehow looks like the true uplift. And if predicted looks like true, then happy days, we're good to go. But unfortunately, if the observed looks nothing like true, then the fact that you're comparing predicted to observed is kind of pointless, basically. And what this means is that there's just a ton of noise when you're doing cross-validation for uplift models. It's just way less stable than using cross-entropy in binary classification. And this makes model selection really difficult. So now let's talk about the kind of methods that people use in practice. And it's broadly about two classes of models called T-learners and direct models. And we've already met T-learners. So the idea behind T-learners, so it comes from simply just two learners. You need some extensions when there's not just offer versus no offer, but kind of offer versus offer A versus offer B. But the idea is that you find all the people who got the offer, all the people who got the treatment, and you find all the people who didn't get the treatment, sometimes known as the control, and you just split them up and you train two different models. And this is what I did a few slides back when I was trying to show you kind of about compounding errors and whatnot. So yeah, I did kind of show you that it already doesn't work that well, but bear with me. So you can use any model you like, but you just need to make sure that these two models use the same sets of features. You can even do something like say, oh, well, much more people in the control group, so we'll use a more expressive model, fewer people in the test group, so we'll use a different model. You could have a logistic regression for one and a random forest for the other. Possibly not a good idea, but you could do that. Direct models take a very different approach. So direct models try to use empirical uplift as the thing that mimics true uplift. And thus they try to basically split the training data up into different groups, which have maximally differing empirical uplifts. So one way of doing that would be you have all of your data and you split it in two. And then, so we've kind of talked about this already, but to be explicit, here I've got some formulae for empirical uplift. So I take the average of the target in the treated group, and I subtract off the average of the target in the control group. So that's the uplift here in the left node, the left data source. And here on the right, likewise, I calculate the average of the target in the treated group, and I subtract off the average of the target in the control group. So how good this split is, there's a couple of different metrics you can use. This is kind of the most simple one. You just take the square difference of the two uplifts. And the idea is there'll be some empirical uplift across your whole data set, and that's what's known as the average treatment effect. But what you want to do is find groups on which the conditional average treatment effect differs from the average treatment effect, or less abstractly, if across your entire population, sending out an advert has some effect, you want to find two subpopulations in which in one of them, the effect is much higher than average, and in one, the effect is much lower than average. And you can then borrow from supervised learning, in particular from decision trees, and use decision trees to partition your space. So this will be one partition. And you brute force search over various partitionings, find the one that gives you the best split of uplift. And then once you've locked that in, then you recursively do the same in each of the created nodes, and you have some suitable stopping criterion. Just to give you a bit more intuition. So if, for example, here, the blue people are the treated and the red are the control. You want to avoid splits like this. And the reason for this is that in this case, so there's not very many treated people, this estimator of the average of the target variable in the treated becomes kind of a not very robust estimator. And likewise over here, the average of the target in the control group becomes a not very robust estimator. So you just overfit very easily. So the way you tend to mitigate this is to use hyperparameters that are very similar to standard decision tree learning. But in standard decision tree learning, where you might have some parameter like min sample leaf to tell you when to stop splitting, here it would be min sample treatment. So not only does your leaf need to have a certain amount of data points in it, it has to have a certain amount of data points per treatment. And that generalizes pretty naturally if you're not just doing treatment and control, but you have multiple treatments. It's kind of min sample per treatment. So I'm going to compare the T-learner to the uplift tree, and what's quite nice, there's a bit of a framework that says the strengths of one of the weaknesses of the other, and vice versa. So the nice thing about the T-learner, you can use any model. So as a guy who works in the consumer space, I'm going to smirk and say in reality that means you can use XGBoost, and that's great. But of course, that might be oversimplifying it. You might have good reasons to believe that logistic regression or neural networks better describe your data, and that's fine. You can just plug that in. So the problem with the uplift tree anyway is that you have to use decision trees, and they're not that optimal for learning complex decision boundaries. In a T-learner, as long as you don't use a decision tree for the T-learner, as long as you use something like XGBoost or a neural network or logistic regression, it can interpolate, so everyone can get their own score, whereas the uplift tree sorts everyone into buckets, and thus you get like discrete scores. Although this can be mitigated because you can do the analog to random forest. You can bootstrap aggregate your data and train an uplift random forest. So that does mitigate it a bit, to be fair. The real problems with T-learner are that A, the model's cost function is not necessarily well aligned with what you're trying to do. And in fact, like the T-learners, they're just trying to maximize your log likelihood. They know nothing about uplift. It's just kind of a side effect. They learn a bit about uplift. And also, as we saw many slides back, the fractional errors can be enormous if the signal is weak. For uplift trees, on the other hand, the model's cost function is better aligned with what you're trying to do. Like the cost function is basically uplift. And you can make it quite robust to overfitting using pretty interpretable hyperparameters. You can just up or down this min samples leaf, and that gives you pretty continuous control over whether I want to overfit or underfit. Final point that I didn't know quite how to fit into this framework was that I expect uplift trees not to handle known confounders very well. By no means will T-learners handle them perfectly, but my intuition on this is that if you have a bit of confoundedness in your data, the T-learner will be more robust than the uplift tree. But unfortunately, I don't have any data to back that up just yet, so it's just a hunch for now. So finally, what are we doing at faculty? We're doing some research on all of this stuff in the hopes of making it better. So for T-learners, what we've really focused on is that the fractional errors can be enormous if the signal is weak, because that's the hardest thing. And the way you should think about this, if you have two models, is what can happen is you have a model for the treated and a model for the controlled. And for a certain part of the space, models are always overfitting. They're sort of getting close, but they're always overfitting around the true signal. And maybe the treatment model overfits a little bit that way, and the control model overfits a little bit the other way, and then you take the difference and it all blows up. And really what you want is to add some mechanism into your training by which when this model fits that way, the other model tends to come with it. So I showed you before in terms of more math, I showed you the propagation of error formula. I mentioned that this is only true when the errors are uncorrelated. If you can correlate the errors of the individual learners, then you should tend to get this effect where when one overfits, the other overfits in the same direction, and when you take the diff, it all cancels. So that's the idea, that we're trying to train T-learner models which are not entirely independent, which bring in some correlation. And there's ways of doing this tree-based, so XGBoost, and we're also looking into deep learning versions of this. But likewise, we're also looking at empirical models. And the idea here is you need some way of partitioning up the space and finding groups in the space which have differing empirical uplifts, and decision trees are one way of doing that. But we're also looking at using representation learning to do this. So whether you can instead represent your data in some sort of latent space, and then probably use something akin to KNN, but KNN in the real space has all sorts of problems with Euclidean distance, and hopefully Euclidean distance will make a lot more sense in the latent space. So that's some of the ideas we're working on there. And a real proof of these methods will be how they deal with known confoundedness, because sometimes you're in the privileged position where you can run a test before getting started, but sometimes you really want to train an uplift model on observational data. So I think I touched on this earlier. For a T-learner, it'll make unreliable predictions when you have high levels of confoundedness. So if you always send offers to certain types of people and not to others, if you ask what would happen if you sent an offer to the type of person you've never sent an offer to before, it's going to be unreliable, but it won't tell you it's unreliable. But if you can change that and make the T-learner actually say, oh, hang on a minute, I'm not sure what's going on here, that can be useful for two reasons. And the first of those reasons is you can kind of say, okay, I'm not going to use the model for this. I'm going to fall back on some unknown business rule. Or you can use that to inform your trial. So you can say, I don't want to run a broad scale trial on all of my customers, just throwing out offers left, right, and center, because that's expensive. But when my model says, look, I really don't know, I need some more information, that's where you have to test. It gives you kind of a pointed and thus more efficient economically way of doing your tests. So we definitely don't think it can be mathed away, right? Like if someone says, oh, I know how an offer will perform on a type of customer that I've never sent this offer to before, you should definitely be skeptical. Somehow axiomatically true, but that doesn't mean that you should just listen to the model. There's other things you can do. And yeah, broadly speaking, we're sort of looking into how the models degrade as well under confoundedness. And my theory anyway is that T-learners will degrade less, but that kind of remains to be seen. So yeah, there's the three things we're working on. Confoundedness, because that's the real world. It's usually confounded. You often don't have trial data. So if you want to actually do this in practice, you need to understand how your models work with confounded data. And then we're looking at making the two broad classes of models better and ultimately benchmarking which perform best under what scenarios to know what to deploy when for whom. So final summary slide. Most problems in the consumer space are inherently counterfactual. And that's the only way to really solve them is using counterfactual models. I think people often don't use counterfactual models. They try to just use standard machine learning techniques, and that's a bit square peg, round hole. Uplift modeling might seem like a minor extension to standard supervised learning. So in theory it is, but in practice it's not. It's pretty involved actually. So I hope I've convinced you of that today. There's two broad classes of models, T-learners and uplift trees, and they have strengths and weaknesses almost in antithesis to one another. And at faculty, we're working on making them both better in order to deploy more powerful models for our customers to make better decisions. And I have to say, I've not shown you any results for any of that stuff. It's very much work in progress, but do watch this space. There will be stuff coming. If you're interested in learning more about this, there's 3 papers I've linked to here, which all can serve effectively as literature reviews. So they go forward in time, state of the literature in 2011, 2016, and 2019. They also get more complex as you go, but I'd say they're all reasonably accessible, especially the first one. If you're interested in this more from a commercial angle, I recently wrote a blog about some of this stuff, in particular, like when you can just use a propensity model, how you can squeeze a bit of life out of your propensity model and make it as useful as possible, and when you need to switch over to uplift models. And if you want to get your hands dirty, especially in Python, there's these 2 libraries, CausalML by Uber and EconML by Microsoft, which have some models for doing uplift modeling open source, and they're some of the best out there. All right. Thanks for your attention, and we'll do a Q&A now until the hour. And also, if someone can help me, I don't know how to actually see the questions.
Gary, if you pop up the Zoom tray at the bottom of the screen, you should see the Q&A. I might be at the top of your screen or at the bottom.
Yeah, I can see it. I can't click on it. When I click on it, nothing happens.
Try close your screen, Gary, just close the presentation and might pop up that way.
There we go. Okay, well, I can't be on it and change. Well, anyway. So I have one question, which is, when you take the difference between 2 signals, as you've shown they are messy, does it make sense to smooth the difference by averaging them and then take the difference? Yes, it definitely does. I guess there the question is basically, can you just get more smooth predictions to begin with? So I think that's kind of the same question as when you're doing binary classification and you get this very jagged response. Does it make sense to then actually fit a regression model to your surface? And like possibly yes. And actually I've looked into taking a similar approach, rather than smoothing the individual signals, smoothing the final uplift signal. Somebody has asked, what is your take on the transformed outcome approach, or the double robust methods? So on the double robust methods, I would say I don't have a take yet. It's something that I'm kind of digesting and reading about. I assume we are referring to what the EconoML documentation referred to as double machine learning, I think is the term. Definitely still digesting that one. The transformed outcome approach, I'm highly unconvinced. Just because two things are true in expectation, like you have no guarantees they're true in distribution. So that's my take on the transformed outcome approach. Someone's asked, what are the trade-offs between uplift modeling and reinforcement learning approaches to learn the right treatments? And the trade-off basically is kind of control, first of all. Like, yes, often to do uplift modeling, you need to run some tests, but you can kind of be pretty specific about what you're going to test, right? You can set the parameter of your tests. You can talk to the budget holders and say, this is what I'm going to do. This is what it's going to cost. This is how long it's going to run for. And, I'm not really aware of many examples of where people are happy to just say, let a not accountable reinforcement learning agent just run riot. But I do agree that, of course, if you can do that and you can do so in a safe way, the risks are always higher using reinforcement learning, but I would imagine that the rewards would also be higher. Another question, wondering how the models handle multiple treatments rather than one. Yeah, that's a good question. So this depends a little bit on whether you can interpret your multiple treatments as a continuum or a pseudo continuum or not. So if you're looking at 10% off versus 20% off versus 30% off versus 40% off, you probably want to think of that as a bit more of a continuum. So you want the 40% part of the model to learn more from the 30% than it does from the 10. So I think in those cases they work actually substantially differently, like possibly needing a full-on redesign. When you just have like three different offers, say, so control, offer A, offer B, offer C, then you can see it as kind of a categorical intervention, then it works pretty similarly. So the T learner becomes, well, it's no longer T because T stands for two, but it's a multi-learner. You train a model on all the people who got the control, all the people who got offer A, offer B, offer C. Uplift is kind of no longer really defined. You don't do sort of probability of buy given marketed minus probability of buy given not. You just have the different counterfactual outcomes. And if, for example, the offers are just like they don't cost you money to send out, then you might just find for each person which offer gives you the best outcome. If the different treatments have different costs, it's kind of this scenario planning, right, where you say for each treatment, what's the outcome minus the cost, and then I choose the best one. The uplift trees kind of work pretty similarly as well. Actually, you kind of I think actually that's not quite true. I think the because you're counting the uplift in the node, whereas it now has to do some sort of more like impurity in the node. So it's quite similar, but the cost function has changed a little bit for the trees. I've got a question on if distributions are expected to follow parameterized patterns like the gamma distribution you showed, why not a more traditional approach? Yeah, so I think in the case of if you only had one variable, as we did in the catalog example, then I think clearly the right thing to do would be to fit a logistic regression to both cases and then diff them because they're smooth, right? And lack of smoothness is basically the problem here. Interestingly though, I didn't use logistic models to, or I use some sort of exponential model with a non-uniform or non-unity power rather. So I still suspect if you fit a logistic regression to that, you wouldn't get an ideal fit. Maybe that's a pedantic point, but certainly as soon as you're in 2-3 dimensions, right? Like if you can look at your data empirically and write down a sensible, smooth, functional form, and then just fit the parameters, then for sure, that's likely to give you a much better result for uplift modeling. But like, most of the world isn't like that. You've got categorical variables, you've got interacting variables. It's kind of all higher dimensional, and you lack intuition. So it basically doesn't work. And most of the time, you know, for the individual problem, you wouldn't be fitting something. You'd be using, you know, a random forest or XGBoost. Yeah, I have a question on case studies. I think that one's maybe not quite appropriate to talk about in front of everybody, but I'm absolutely happy to follow up about that one offline. And I believe someone's asked me to go back to the slide with links. All right, I'll continue to leave that one open in case anyone writing them down. And I think that's all open questions answered. So thanks everyone. Thanks for your attention. Thanks for coming today.